Welcome back to Gabversity. Lovely to see you all again. And Gabversity is where you can go fact yourself. All right, absolute pleasure. So what we're going to do now is we're going to look at stationary states, and we're going to look at how to develop the Schrödinger equation, and we're going to look at the time-independent schrödinger equation. I always call it schrödinger. I don't know why. It's Schrödinger. Welcome to Gabversity, where you can go fact yourself. All right, that's it. Welcome, National 90, long time. So let's begin. Now, if anyone's done calculus, you will remember that when you have a multi-dimensional equation, where's the owl? Go fact yourself. There he is. All right, so we can separate a two-dimensional function into, but still will attempt. Okay, sounds like a plan. You can separate them by the method of separation of variables. And what's interesting is that it works in this universe. Mathematics shows us that you can't just separate the variables to get two one-dimensional functions from one two-dimensional function. But in this universe, it works because we only want the harmonic functions. And harmonic functions are the only ones that work in this universe, as you would have seen in the last lectures. You can't go to the top of the stairs without going up something to go back to the top to come down again. You can't just come down the stairs and then go down the stairs again automatically. That doesn't work in this universe anyway. All right, so we're going to do separation of variables. Hey. All right, so what we have here, this is, if you remember, this is X is the one-dimensional space equation, one-dimensional space, right? So at the moment, we're only looking at particles, right, that are sort of moving in one direction or the other. It's not 3D, it's just backwards and forwards, right? And that's the X, and T is time. All right, and now what we can do is separate this. We can have psi and phi. So we can have psi of X, and we can have phi of T. All right, and if you haven't done it, that's fine. But basically, mathematics shows us that you can have a separation of these variables in this big function and separate them into a function of X and a function of T, which is pretty crazy. So that means that now we have a wave function that imagine having a skipping rope, right? And you go like this, and then you freeze time, freeze. And then you can travel around the wave and look at it up and down in one particular instance in time. That's the other one. That's this one. And then this as a function of time that's easy because that's just over time. All right, so now what we're going to do is we're going to use this to figure some things out. So the first thing we have to do, right, is we can let this equal what's next to time. This is a phi. So that's psi and that's phi, but it's just you could put anything you want. You could make that a p, you can make it an f. It doesn't matter. It's just a function. It's a map. Yeah, good question. All right. So what we can do is we can make that equal to a constant, and that constant, let's just call it g. All right. So then we can say, I haven't done this in a year. I should have practiced first. All right, so d of the wave with respect to time. Okay, so now we're going to derive it just with respect to time. All right, we're going to say that equals this one here, all right, multiplied by d phi dt. All right, so that's the wave function, right? The spatial wave function multiplied by d phi dt is the same as saying the whole wave function, only deriving it on the time side. So basically what we've done is we're getting the two-dimensional wave function. We froze one side, and we're looking at what happens in time if we haven't moved it. All right. So if the actual space does not move at all, if the particle freezes, and then over time we look at what happens to the wave, that's this, like the speed in a way. Right? And please come back. There we go. All right. So that's the same equator. Yeah, not too bad. Yeah, that's not too bad. Is that multiplied by the derivative of this with respect to t, right? Which is sort of obvious. And the second derivative with respect to x, right? So the second derivative of the wave function, right, with respect to x, right, is going to equal the derivative of the partial wave function with respect to x, right, which is going to be the lowercase one. So to make this capital, I'm just going to put a line on top of it, just to make it easy, because my font is not the best. All right, somebody bought a calligraphy pen, the same one that I use. That was really cool, but it turns out I don't get commission in Australia because Australia is dodgy. All right, so d2 that, right, over dx squared. So that's the second derivative. Is that the answer to the question on in the last curve, equator? Ah, that's what you meant by equator. Sorry. I thought you meant, how dumb am I? I thought you meant that this was comparing, freezing it is like comparing it to the equator. You did. That was paint something. She's a beautiful artist, by the way. Hello, everyone. I'm not going to tell you till the next lecture, but good question. Go the Patriot, man. He's a man of passion. I love that. All right, multiplied by psi. All right. So now the second derivative of the whole wave is the same as getting the partial derivative, like the space section of the wave, getting the second derivative, multiplying it by the time function. All right. Now, this may or may not make sense right now, but as we do heaps of them, it'll start to make more sense. But the reason we're doing this is because in physics, they're not mathematicians, right? They use mathematics as a tool. That she bought the pen. Yes, she did. Yes. That one I got. Thank goodness I'm not completely slow, right? So my scarf is falling off my head. I'm getting less Middle Eastern. Anyway, all right. So, don't be sorry, my dear. Don't be sorry at all. Sorry. Sorry. All right. So, the point is that we have a two-dimensional wave, right? And we want to break that down as a physicist because we want to make things easier. Now, mathematicians, right, what they do, they design the tools, okay? But physicists use those tools to find the world, what's going on, right? So it's like, one guy makes the wrench, one monkey makes the wrench, the other monkey uses the wrench. So the physics is like the mechanic, I guess, right? Now, so how do you, hey, Patriots is back. How do we make that work? Well, what you do is you separate the variables, right? So this is a two-dimensional wave. So it's a wave it's going like that, right? But it's also changing over time. So it's like that and it's running like this, right? So you've got to look at two different locations. You've got to see where it's going this way and where it's going this way at the same time. And that gets unbelievably complicated, especially when you add 3 dimensions, because then you're going to have this and 3 dimensions and time. It becomes too difficult. So what you do is you can analyze different parts of the wave. So you can look at the spatial section of the wave. So if you freeze time, you just look at, you're doing this, you freeze. And then you can look at that wave frozen in time, right? And then you can not look at the wave and look at the time, right? So you look at them separately. That's what we're trying to do. So we use mathematics to separate all the different waves from each other, right? And physics does that a lot, right? It's how you create radio stations. It's how you have 4G networks with mobile phones. Because basically what you can do is mathematics allows you to peer into the other dimension that we can't see, and you can split a wave. So like a radio frequency is like heaps and heaps of waves, right? Or even your voice, every voice has like heaps and heaps of different waves to make your voice rich, right? What you do is you can look at this wave on the side and then split it up into multiple dimensions that we can't see, and then you can see every different wave that makes up the big wave, right? So it's pretty cool. So that's what we're doing now in mathematics. So now, right? Right? So what we've done is my husband used both as a certified traffic accident reconstructionist. I can imagine he would have to, yeah. That would be very cool. That would be a very cool job. So I'm going to show you the Schrödinger equation again, right? So here is the equation. And this equation is so important because it's the fundamental mapping of particles. You should taught maths when you're in college. Oh, my dear, I wish I knew maths. IH, and then we have the partial derivative, right, of that with respect to time. Okay, so this is the time component, right? And it's basically the derivative over time. We're taking a slice of time. And that's the Planck's constant reduced. And that is the size, basically the size of the pixel of our universe. So whatever God made or whatever, however it was created or whatever, the smallest possible pixel size is this number. And I is the square root of -1. That is the number that brings us into other dimensions. Okay, so this, right, equals negative h squared, right? That's the pixel size squared, over 2 times the mass. Okay, multiplied. I have to be a bit quiet because everyone's asleep now. It's late here. Multiplied by the partial derivative of psi. Actually, I keep forgetting I've got to put a thing to make it capital. All right, and the second derivative with the spatial derivative, second spatial derivative, right? Plus the potential energy. What would that equation look like with Common Core math? It would probably read feelings. Feelings come before facts. Oh, that's funny. And you just say to them, go fact yourself. That is our new line. I learnt that line from Pompous. Go fact yourself, bitches. All right, so this is the equation of Schrödinger. And this equation is how you map anything that makes us up. We're made up of quantum particles. Those quantum particles are actually waves. So we're made up of waves. And how do you track those waves using mathematics? With that equation. All right, so what we're going to do is, now that we've been able to convert a few of them, we're going to slide them in. Right? So we now know that that equals that, right? And we know that that equals that. So we're going to slide them in here. And the reason is because we want to separate the equations. So that is the full equation. That's the full 2-dimensional equation with time and 1 dimension of space. What we're doing is we're sliding in the splits. And by putting the splits in, then we can pull out the spatial part and pull out the time part. So similar to what your husband would have done with, he would have had to reconstruct all the location of the cars with time to each second that passed. Where was each car and where was each car going? Where was each car going would be the derivative. Yes, because the speed of the cars would be the derivative. The acceleration of the cars would be the second derivative, right? And then at each location, that would be time. So after 1 second, the cars are moving this way, which means dx, ddx, yeah, derivative of the equation with respect to x, which is the space one, it has changes over time. Yeah, so there you go. All right, so now what we're going to do is we're going to slot these, right? So that equals that, right? So we're going to put that into here. Okay, it's pretty simple. We're just going to put that into there. And then we're going to put, if you look at this, there, that equals that. So we're going to put that into here. That's it. It's like Legos. We're just swapping the pieces. And then we just have to divide by this and by this. So I'll do them both for you right now. So this is now going to change, right? This is going to become IH bar, and we're going to take that and we're going to put it in here, right? Which will be lowercase psi partial of d phi dt. Looks like Chinese to me. Oh, that's racist, man. That's it. It's all over. You're going to get sacked. Too funny. Man. So that equals, right? So remember, as we said, this is the number of alternate dimensions. This is the smallest pixel in our universe that can exist. Here is the wave function multiplied by that, which is the derivative with respect to time. Right? So how fast is time going at certain places, for example? You could sort of say that equals minus h squared over 2 times the mass of the particle. Right? And then let's replace that with that. So we're going to have d2 psi dx squared. So that's the second derivative of the space dimension of the wave. Right? Okay. And then there's going to be a phi, which is the time section, all right, plus potential energy of the whole wave. So here, if you remember, this multiplied by that, because as we said, we're treating the whole function as multiplication of the space function by the time function. And that only happens in this universe. This equation only works in this universe so far, because mathematics shows us that outside of this universe, this breaks down. That's not the complete truth, which is very interesting. So now, there you go. That's our thing. All right. So now, what's going to happen is that let's divide by psi and phi. And if we divide, we're going to divide by psi and by phi together, right? And the only reason we're going to do that is just there's more than one universe. Mathematics tells us that that's probably true. Yeah, there's probably an infinite amount of universes, but we can't prove it. Yeah. So there's lots of Patriots United. There could be stupid blurring. There could be a Patriots United that is like pro Hillary or something in another universe. And it could be that Hillary was the Republican and Trump was the elitist, And you don't know. 1 over phi d d phi dt. All I'm doing now is just playing Lego with mathematics. This is not that difficult. We're just, you add one from here, you take it from there. It's like a seesaw. And this stupid freaking blurriness is so bad. There we go. Right? Equals negative h squared, or h bar squared, over 2 times the mass, 1 over psi, multiplied by d2 lowercase psi dx squared plus v. So we're just playing Lego, as I said, All we did was cancel. Okay, now if you notice something that's interesting, what we have done, let me show you what we've done. Let me just put the lid back on this again. Have a look. This side only has t on it, right? Look, and that's a function of time. So that's time, and that's a derivative with respect to time. This is only space, because that's the space function, and x is to do with space, and that's just potential energy, right? So that's space, and that's time. Now, how can two functions be equal if they're completely different functions? This is a mathematical concept, right? I'll give you an analogy. How can the ticking of a clock be the same as a heartbeat? Only if they're both ticking at the same speed. Rutheniums. Rhythms. Yeah, rhythm. So they have to be at the same rhythm. Otherwise they can't be equal. That is not a proof. That is just trying to explain it in regular terms. Synchronized, yeah. Synchronized. So in mathematics, synchronizing, it's called a constant because they're always staying the same with each other. So there's no difference, which means there's no acceleration. So if, for example, you're in one car and someone else is in another on the highway, the only way you could talk to each other through the windows is if you're both traveling at the same speed. Otherwise, you'll be going past each other, what are you going to do? You know what I mean? Backwards and forwards, right? So that's the same what's happening here. We have two different functions. One's time and one's space. How can they be equal to each other all the time? The only way is if it's a constant. Exactly. So that is exactly what we're going to do. So that means both sides have to equal one particular constant. Okay. For reasons that will appear, we shall call the separation constant E. Okay. So now what we're going to do is we're going to say, well, they're both traveling at the same speed. So now let's look at that particular speed, because now we could bring in another car and keep that at the same speed as well, right? So we know that if we concentrate on fixing that speed, then we can get heaps of cars, as long as they fit on the highway. Heaps of cars can actually travel in a group if we have one thing in common, which is the speed. So that speed, right, is the thing that's constant. That's how you can talk to someone else. And so when you have a function of time on one side and a function of space on the other side, the only way they can stay in sync is if they're constant. And what's the constant? It could be speed. It could be, like with cars on a freeway, it's speed, right? With here, we don't know what it is yet. It's something. So we could call it something. But to save space in mathematics, because we're lazy, instead of saying something, we're going to just call it E, all right? Just to make it easy. Right? So what we're saying is that here is one car and here is the other. And the only way they're staying in sync all the time, because they're obviously equal, right, from the mathematics, is that they are traveling at some constant something. And that something, we're going to say I h bar 1 over phi d phi dt equals something, right? And we're just going to call it for now E. So this E is something, right? But it also equals that minus h bar squared over 2m 1 over psi second derivative of, did it again, psi over dx squared plus v. Okay, so now we've separated them. That equals that, and that equals that. That's two different equations. We can say that equals that, and we can also say that equals that, which is pretty awesome. And you're going to see why it's awesome in a sec. Right? So what we have done, this is the space section, remember? So now we can say that the space section of any quantum particle, which is this part here, 1 over psi d 2 psi dx squared plus the potential energy, that equals E. There you go. So what we have proven that this equation is a constant. Okay? What does that mean? That means that we have captured the space equation independent of time. So what we have done, remember how we said with the skipping rope, and you freeze it? Now we have frozen it, and it's just the space, so we can track where the particle can go, but we've frozen time so we can look around it everywhere, right? And we can check how the particle would move, all the potential locations of the particle that it could be at one snapshot. It's like taking a photo. So what we've just done, we've just taken a mathematical photo, and that is brilliant, because now even if we don't know the time, we have all of the information. So if we have the mass of the particle and we have the particle's location, we can find out the particle's energy, right? Which is awesome. So it's the same as what we did was, you're driving down the street and another car is driving down the highway. You're both going down the highway. Because you're able to talk to each other, then you must be going at the same speed. So now, even if there's no one there, we now know that one of the cars is traveling at a constant speed, which means acceleration is 0. Right? That's brilliant, because that helps eliminate a lot of the problems. We can focus just on what's happening inside the car. Basically, that's all we've just done. So that ends today's lecture. What we're going to do after this is I'm going to show you how to backwards. So instead of backwards deriving, it's called integration. So we've done integration before. You've seen it where I've had the thing, right? Integration is going backwards. Yeah, integration is a step backwards. Yeah, exactly. Instead of a step forward, it's a step backwards. So if you have the car's distance, right, then you could find out the car's speed. If you have the car's speed, you could find out the car's distance, right? So you can go backwards, right? So going forwards would be distance, speed, acceleration. Going backwards would be acceleration, speed, distance. So backwards deriving, do you do this for fun? I do this for fun, yeah. But I'm actually doing I'm doing a degree, yeah. So, but it is fun for me, yeah. So what we're going to do is we're going to go backwards, and then I'm going to show you what mathematically integrate rewound. Very nice, very nice. And then because now what we've done with this mathematics, we're now able to get the equation of the wave itself. So what we'll be able to do is we'll get the equation and we can draw the equation, which means that you can draw exactly every point that the particle can go, right? It's basically a map. It's a map of like an imaginary city, and each particle has its own map, and they can only go certain ways, right? So that's it. That's what we're going to do in the next lecture. So I'm probably going to go get some sleep now, and then I'll get up early morning and start again. And don't forget, Gabversity, where go fact yourself.